Welcome to the deep dive. We're diving into the world of actinium today.
Oh, yeah.
You with me?
Absolutely. I am fascinated by this element.
I think it's going to be a really fun journey.
Yeah.
For our listeners, actinium, you may or may not have heard of it. But it's one of those things where it has a really fascinating history.
Absolutely.
Some really, really cool properties.
Yeah.
And it has some potential for some really cool breakthroughs in different fields.
For sure. It's one of those elements that often flies under the radar, but
Right.
there's some really interesting things about it.
So what is it?
So actinium.
Like if I were to hold it in my hand. Well,
Okay, well, first of all, don't hold it in your hand.
Okay.
It's radioactive.
Okay.
It's a soft, silvery white metal.
Okay.
But here's the thing, it glows in the dark.
Yeah.
With a pale blue light.
No way.
Yeah. And this is because the particles it's emitting are actually ionizing the air around it, and that causes this luminescence.
Whoa. Okay, so it's like its own little light bulb.
Kinda, yeah.
That's so cool. Okay, so glowing metal. Check.
Yeah.
Now tell me about the discovery. You said two scientists.
Yeah, so we start in 1899 with André Louis de Bierne,
Okay.
who was a French chemist,
Okay.
and he was working with pitchblende,
That's
which,
familiar.
yeah, it's the same material that Marie and Pierre Curie
Right. For radium.
used to isolate radium, exactly.
Wow.
And de Bierne believed he found a new element in those leftovers, and he called it actinium.
So he's like digging through the trash, basically.
Kind of, yeah. He's looking at what else is there, and bam.
Wow, that's amazing. So two scientists, you said.
Yes. A few years later, in 1902, a German chemist named Friedrich Oskar Giesel independently discovered actinium, and he was actually able to isolate it in a pure form, which is amazing for the time.
Oh, wow.
And being very impressed by the radioactivity, he named it amanium,
Okay.
which means to give off rays.
Okay, so we have these two different names from two scientists.
Right.
Who gets the credit?
The credit ultimately went to de Bierne because he was the first.
That's it.
But Giesel's work was so important to really solidify that it existed as an element.
Right. I mean, isolating it is huge.
Exactly. And it was because of Giesel that we know the atomic number is 89.
Okay, so de Bierne gets the naming rights,
Yeah.
actinium, from the Greek actis, meaning beam or ray, which makes sense.
Absolutely.
Very radioactive.
It is.
Okay, so besides the glowing, what else makes actinium unique?
Well, actinium actually behaves a lot like another element on the periodic table, lanthanum.
Okay.
And this makes separating actinium from ores really difficult because they tend to cling to each other.
So it's hard to extract it.
Yeah, it's a challenge.
I mean, it's already super rare, right?
Yes, incredibly rare.
So you'd think there wouldn't be a ton of uses.
Yeah, so the scarcity and the radioactivity does limit industrial applications,
Hey.
but it has huge potential, particularly in medicine.
Really?
Oh, yeah. This is where it shines.
I'm intrigued, but before we get there,
Yeah.
isotopes, right?
We have to talk about isotopes.
Okay, so remind me again what an isotope is.
So isotopes are basically atoms of the same element,
Okay.
but with a different number of neutrons.
Okay.
So you can think about them like siblings with different personalities, but they're all in the same family.
Okay, I like that.
And when it comes to naturally occurring actinium, there are two main isotopes,
Okay.
actinium-227 and actinium-228.
What's the difference?
So actinium-227 is a member of the uranium-actinium decay series with a half-life of about 21.7 years.
Okay.
And it primarily decays through something called beta emission,
Okay.
but it can also sometimes release alpha particles.
Okay.
Actinium-228, on the other hand, is part of the thorium decay series, and it has a much shorter half-life, only about 6 hours.
Okay.
And this one undergoes beta decay.
Okay, so one is a little more lively than the other.
You could say that.
I'm going to guess both of them are pretty hard to find.
Yeah, extremely rare.
Okay.
We're talking trace amounts in uranium and thorium ores. So, to give you a sense of the scale, for actinium-227, you would need a ton of natural uranium ore
Wow.
to extract a measly 0.2 milligrams of actinium-227.
Okay.
And if you're looking for actinium-228, you'd need a ton of thorium to get 5 nanograms.
Oh my gosh.
It's like finding a needle in a haystack.
It really is. So if it's that rare,
Yeah.
how can it have any significant application?
Well, that's a great question, and the answer lies in the unique properties of specific actinium isotopes.
Okay, this is getting good.
Yeah.
I can't wait to find out more.
We'll dive into that in part 2.
All right, I'm ready when you are.
So before we dive into applications,
Okay.
I think it's important to emphasize that actinium, especially actinium-227, demands a lot of respect.
In what sense?
Well, its radioactivity means that when you're handling it,
Oh, right.
Specialized laboratories and safety precautions are a must.
So this isn't something you just whip out in your basement?
No, no, no. We're talking like airtight glove boxes, hot cells with thick shielding
Wow.
to block that intense radiation. Yeah, serious stuff.
Makes sense, though.
Yeah, but let's shift gears back
No.
to the applications of actinium, particularly in medicine
Okay.
for cancer treatment.
Right. Right. Using it almost like little tiny missiles to deliver radiation directly to cancer cells.
Exactly.
That's incredible.
Yeah, so it's called targeted alpha therapy.
Okay.
But how do they actually attach?
Right. Yeah. How do you get it there?
That's a great question. So it's all about chemistry.
Okay.
So actinium, its oxidation state is +3, which means it readily loses 3 electrons.
Okay.
So it really wants to form bonds.
Okay.
And that's where these chelating agents come in.
You mentioned those before, yeah.
These molecular claws,
Right.
grabbing hold of the actinium and holding it tight.
Okay. So we've got our actinium all strapped in.
Right.
But how do they, I mean, it's got to get to the right place.
Exactly. And that's where antibodies come into play.
Okay.
You know, these are the remarkable proteins that are actually part of our immune system.
Right.
And they have this incredible ability to recognize and bind to very specific targets,
Oh, wow.
like a lock and key.
So each antibody goes
Sure.
to a certain spot.
Yes. So in this case, the keyhole would be a unique marker
Right.
that's found on the surface of the cancer cells.
So it knows where to go.
Exactly. So by attaching that actinium-carrying chelating agent to an antibody,
Right.
you're essentially creating these targeted missiles.
Wow. It's like a little GPS system.
It is a GPS system programmed with the cancer's address.
That's incredible.
And the beauty of this approach is that it allows for incredibly precise delivery,
Right.
minimizing damage to surrounding healthy tissues.
That's the key.
Yeah, so what kind of results are we seeing?
Yeah. Are we actually seeing results?
So it's still early days in terms of widespread clinical use,
Okay.
but the initial results are very encouraging.
That's amazing.
Yeah, studies have shown effectiveness against a range of cancers.
Wow.
From leukemia and lymphoma to breast, ovarian, and even prostate cancer.
Oh, wow. So a wide variety.
Yeah, but I imagine there are still challenges to overcome.
Right. Yeah.
Yeah.
It can't be that easy.
No, it's not. One of the biggest challenges is actually preventing
Oh.
the actinium from accumulating in healthy tissues.
Right. Because it's still radioactive.
Exactly. So particularly the bones and liver are sensitive.
Okay.
And so even though the therapy is targeted,
Right.
there's always a risk of some of the actinium ending up where we don't want it.
So how are they working on that?
Well, researchers are always experimenting with different chelating agents,
Right.
trying to find the ones that will minimize that unwanted accumulation.
Okay.
And they're also working on ways to improve the body's own natural clearance of actinium.
Oh, so the body can flush it out itself.
Exactly.
Okay. So it's like a constant battle to sort of refine it.
It's a constant process of refinement and optimization.
Wow. It's incredible, though, how they're taking this element and really making it useful
Oh, yeah.
for something so important.
And remember we talked about its role in oceanography
Oh, yeah, yeah.
as a tracer to study ocean mixing.
Right. Using it to figure out how the ocean is moving around.
Exactly. And this is really important for a lot of reasons.
Okay.
It impacts things like climate patterns, weather forecasting,
Wow. So
even the distribution of nutrients and marine life.
it's all connected.
It is, and actinium-227 and its decay product, thorium-231,
Okay.
give us this unique window into these processes.
So you mentioned that actinium kind of moves up
Right.
and then the decay product sinks
Yeah.
to the ocean
Mhm.
floor. So how do they actually track that?
Well, it involves collecting water samples at different depths.
Okay.
Sometimes they use specialized instruments that are lowered from research vessels,
Wow. Okay.
and then they bring those samples back to the lab
Right.
and analyze them to detect these tiny traces of actinium and thorium.
Like a little vertical map.
It is. It reveals the hidden patterns
Right.
of mixing.
So what are they learning from that?
Well, it's helping them to refine climate models,
Okay.
predict how pollutants might move through the ocean,
Wow.
and even understand how marine ecosystems function.
So like how do things get from the bottom of the ocean to the top?
Exactly, like nutrients, for example.
Right.
We can better understand the factors that influence the health of fisheries.
It's amazing how one element
It is
that was discovered back in the day
over a century ago.
can play such a huge role in all these different areas.
It really is.
From cancer treatment to understanding our oceans.
And who knows what else?
Right, exactly.
It's a story that's still being written.
Well, on that note,
Yeah.
we're We're going to take a short break.
Okay.
But join us for the final part of our actinium deep dive.
All right.
We'll see what the future holds.
Sounds good.
So we've gone through this incredible journey.
We have.
With actinium.
It's amazing.
From glowing in the dark to potential cancer treatments.
Right.
Even to learning about our oceans. So what now?
What does the future hold?
Yeah. What's next for actinium?
Well, it's really fascinating to think about.
Yeah.
I mean, it might not be a household name.
Right.
But all of this research we've talked about suggests that it's going to have a much more prominent role in the future.
What ways?
Especially in medicine.
Okay.
That targeted alpha therapy.
Right.
That could really be revolutionary in cancer treatment. But it doesn't stop there.
Okay, so what else? What else are they looking at?
Well, there's some really exciting research happening where they're using actinium-225 not just for its own radioactivity, but as a source to produce other medically useful isotopes.
Oh, wow. Oh.
So remember how we talked about it decaying to bismuth-209?
Right, the non-toxic one?
Exactly. Well, along that decay chain, it also produces other isotopes. And some of these could be really useful therapeutically.
So it's like it's a stepping stone.
It is.
To getting to other things.
Exactly.
Wow, that's incredible.
And then on the therapeutic side of things, researchers are always working to develop new, more specialized chelating agents.
Right.
Those molecular claws.
To grab onto it.
Exactly. And the goal there is to create agents that bind even more selectively to actinium. So you can really increase the precision and the safety of the therapy.
Wow, so less side effects.
Yeah.
More effective treatment.
Absolutely.
That's a win-win.
It is.
So beyond medicine, are there any other fields where actinium could be a game changer?
There are. So in material science, there's growing interest in actinium's potential role in superconductivity.
Now that sounds futuristic.
It does a bit, doesn't it?
It does, but remind me what superconductivity is.
Yeah, so it's basically where you have electricity flowing with zero resistance.
Isn't that something that only happens in like really cold temperatures?
So right now, yes. It's mostly observed at extremely low temperatures, which limits its practicality.
Right. I mean, how are you going to keep things that cold all the time?
Right. But the exciting thing is there are theoretical predictions that suggest certain actinium compounds, particularly hydrides under high pressure, could exhibit superconductivity at much higher temperatures.
So you're telling me this thing that was discovered, digging through the leftovers,
I know,
could change how we get our power.
It could. And imagine highly efficient electronics.
That's incredible.
It is. It's amazing.
It really shows you that you never know what's going to be important.
Right. And what will have these huge impacts on completely unrelated fields.
Yeah. I mean, who would have thought?
I know.
So this deep dive has been amazing.
It has.
I've learned so much
Me too.
about this element that I had never even heard of.
And there's still so much more to learn.
That's the exciting part.
It is.
That we don't know what we don't know.
Exactly.
So to our listeners, I would encourage you. Actinium, keep an eye out for it.
Definitely.
It may not be a household name right now, but with its potential for medicine, for energy,
like technology,
it could really shape the world of tomorrow.
I think so too.
This has been another great deep dive.
It has.
And to our listeners, thank you so much for joining us.
Thank you.
Keep that curiosity alive, and we'll see you next time.
See you then.